Something happened this week that should not have happened yet. Not like this. Not in early March. And the fact that it did, the fact that the atmosphere organised itself into full outbreak mode weeks ahead of where the calendar said it should, is the kind of thing that makes scientists pause, pull up their data, and stop and take a closer look at what the data is actually showing. If you live anywhere in the middle of this country, you may have noticed temperatures running well above normal in the days leading up to this outbreak, warmer than early March typically feels in this region. And then, without the weeks of slow build-up that usually precede the first major outbreak of the season, it arrived. Stay with me for the next several minutes because we're going to cover exactly why this outbreak came so early, what the atmosphere was secretly doing for weeks before the first storm cell even formed, how a fading ocean cycle and an invisible event far above the clouds quietly set the stage for all of it, and what scientists are actually forecasting for the rest of this spring, not in vague, cautious language, but in plain, honest terms you can use. Hit the like button right now, subscribe so you don't miss what comes next, and drop a comment telling me where you're watching from. Because what you're about to learn over the next several minutes is directly relevant to where you live, whether you're in a state that has always been on the severe weather map or one that hasn't been. Because here is the question that nobody in mainstream weather coverage has actually answered yet. It is not what happened. We all saw what happened. The real question is why it happened when it did weeks before the season was supposed to reach this point, and whether this is a one-time early arrival or the opening signal of something much larger that has been building slowly beneath the surface of our weather patterns for years. There is a chain of events, some happening in the Gulf, some happening at the edge of the stratosphere, some happening in the deep ocean that set all of this in motion long before the first warning was ever issued. When you understand that chain, the event that just happened stops looking like a random early arrival and starts looking like the predictable result of a pattern that has been quietly shifting for years. But we have to start at the beginning. Not with the storms themselves, those you've already seen. We have to start with the atmosphere, and with a question worth taking seriously if you pay attention to how weather actually works. Why was the air in this part of the country already primed for severe weather before the typical season peak? And why did so few forecasters catch it until the window was nearly closed? That answer begins with something Climate Central confirmed in its March findings, and what you're about to hear will change how you read every severe weather headline for the rest of this spring. And let's go back to the days before the outbreak. Not to the moment the storms formed, to the days and weeks before that, when the atmosphere was quietly building towards something most people didn't see coming. Because what happened in early March was not a surprise to the atmosphere. The atmosphere had been loading for this moment for a long time. The surprise was entirely ours. The setup began with temperature. Not the kind of temperature that makes a news headline on its own, not record-shattering numbers, not something people would necessarily notice day to day, but a slow, persistent warmth running across the southern half of the country that was running well above what early March typically looks like in this region. Climate Central's data from this period confirmed what many weather observers suspected. The air masses involved were not behaving like typical early March air. They were warmer, more unstable, and carrying significantly more moisture than the calendar suggested they should. You have to understand what warmth does to an atmosphere that's trying to stay stable. It loads the atmosphere with stored energy. When that energy builds up between competing air masses, it eventually has to be released, and in the right conditions, it releases fast and powerfully. When you have unusually warm, moisture-rich air flowing north from the Gulf at the same time that a sharp cold air mass is diving south along the jet stream, and that collision happens weeks before the typical mid-spring window, you get the kind of atmospheric setup that scientists describe as explosive, not in the sensational sense, in the literal atmospheric physics sense, energy that has no stable path, that releases quickly and forcefully when conditions reach the right point. That trigger was the jet stream. And this is where things get genuinely interesting, because the jet stream in early March was not behaving the way it typically does at this time of year. Rather than sitting in a position that keeps cold and warm air properly separated the way it usually does through the early weeks of spring, it dove sharply southward in a configuration that compressed the boundary between those two air masses into a narrow zone over the central United States. Here is what made this early. That configuration typically doesn't arrive until later in the spring, when the sun angle is already higher, when the Gulf moisture is already running deeper, when the atmospheric contrast between north and south has had more time to build. In early March this year, the jet stream moved south sharply and found an atmosphere that was already warm, already unstable, and already carrying enough moisture to produce a full outbreak response. and Climate Central's findings from this period made something very clear. The temperature departure from normal in the days leading up to this outbreak was not a small or incidental detail. It was the foundation on which everything else was built. The warmth was not seasonal warmth. It was a structural anomaly, a sustained above-normal pattern that had been building for weeks, and that turned what might have been a modest early-season event into something the National Weather Service was characterizing as the season's first widespread outbreak threat. What made it particularly difficult for forecasters to fully anticipate was the speed with which the jet stream moved into position. The window for predicting a severe weather outbreak of this kind is already narrow. The atmosphere moves and changes faster than models can always capture at extended range. But when the jet stream configuration develops faster than the seasonal norm, that window narrows further. Forecasters were working with compressed lead time. They saw it coming, but not with the runway that a mid-spring outbreak typically allows. And here is the detail that connects this to something bigger. The warmth that loaded the atmosphere in early March did not come out of nowhere. It was the result of an ongoing atmospheric pattern that had been running above normal for an extended period before the outbreak week. That pattern was not random. It was being driven, at least in part, by forces operating at much larger scales than a single week of weather forces connected to the ocean, to the stratosphere, and to a shift in the atmospheric circulation that scientists had been watching for months. You may have noticed, if you follow weather at all, that this winter had an unusual quality to it. Warmth came in spikes that felt out of place. Cold returned in surges that felt equally jarring. The atmosphere seemed to be swinging between modes rather than settling into one. That is not a coincidence. That is a symptom of a large-scale atmospheric transition, one that removes the quiet, stabilizing forces that normally keep early spring from going straight to outbreak mode without building slowly toward it. The atmosphere this week was not behaving like early March. It was behaving like a later season, high-energy setup that arrived a full chapter too early. And when you understand why the atmosphere was in that condition not just at the surface, but at every level from the Gulf all the way up, the early timing of this outbreak stops being mysterious. It starts being completely logical. But warm air and a sharp jet stream can only explain so much. There is a larger force that removes the atmospheric brake that normally keeps early March from reaching this kind of intensity. And to understand what that force is, we have to talk about something that most weather coverage hasn't touched: a shift in the global ocean pattern that scientists had been tracking all winter. That reached a critical turning point right at the moment this outbreak was forming. Here is something that will reframe everything you just heard. The atmospheric setup, the warmth, the jet stream configuration, the early season energy did not happen in isolation. It happened at a very specific moment in a much longer story. A story about the ocean and about the particular way the atmosphere behaves when the ocean transitions from one phase to another. The ocean phase in question is La Niña. If you follow long-range weather coverage, you've heard the term, but most people hear it as background noise, a distant technical condition that affects weather in abstract ways. What most coverage doesn't explain is how La Niña's exit from the picture changes the atmospheric rules in a way that directly sets the stage for what we just witnessed. La Niña, at its core, is a cooling of the surface water in the central and eastern Pacific Ocean. That cooler water changes the way the atmosphere moves over it, and that change ripples outward across the entire global circulation pattern, including, critically, how the jet stream positions itself over North America during winter and early spring. One of the effects of La Niña is that it tends to keep the jet stream in a configuration that limits how often the atmosphere over the central United States locks into classic severe weather mode. It's not a perfect shield, but it acts as a kind of quiet stabilizer that keeps certain setups from fully developing. When La Niña exits, and particularly when it exits quickly, as it has been doing in early 2026, that stabilizer disappears, the atmospheric rules change. The jet stream is no longer being nudged into the same configuration. It becomes freer to swing, to dive, to create the sharp north to south contrasts that fuel intense spring weather. NOAA's Climate Prediction Center was already tracking this transition by early 2026, noting that a shift from La Niña toward neutral conditions was underway, with the transition expected to complete in the late winter to early spring window. AccuWeather had flagged this transition months before the outbreak occurred. Their pre-season forecast for 2026 specifically identified the rapid exit of La Niña as a key factor, one that would reshape the atmospheric pattern for spring in a way that forecasters needed to watch closely. The language was careful and measured, as it should be in any responsible long-range forecast. But the warning was there. The transition from La Niña was expected to remove a stabilizing influence at exactly the moment when the Gulf was starting to pump warm, moist air northward. Think of it this way. During La Niña, the atmosphere has a bias, a tendency to settle into certain patterns more often than others. That bias keeps the spring, severe weather season from ramping up before it's supposed to. When La Niña fades, that bias fades with it. The atmosphere becomes more volatile. It loses its preference for one pattern and becomes more susceptible to whatever forcing mechanisms are operating at a given moment. In early 2026, the forcing mechanisms pointing toward a significant outbreak were already in place. What made this transition particularly impactful was its speed. La Niña didn't fade gradually. The exit was rapid. Rapid enough that the atmospheric adjustment happened in a compressed time frame, meaning the circulation patterns that typically evolve over months had to rearrange themselves over weeks. That kind of rapid transition is historically associated with more volatile spring weather. Not because the transition itself causes tornadoes, but because the atmospheric patterns that emerge during rapid transitions are less predictable and more prone to sudden, intense reorganization. AccuWeather's spring 2026 forecast captured this dynamic directly. Their long-range team noted that a rapidly fading La Niña and a slower jet stream would be shaping the weather patterns through the early part of spring, a combination that, when coupled with above-normal warmth already in place, creates the atmospheric conditions that produce exactly the kind of early-season outbreak that just happened. There is also a historical pattern worth understanding here. When La Niña transitions to neutral conditions during the spring, the tornado record shows a tendency for the early part of the season to overperform, to produce significant events earlier than the calendar would typically suggest. This isn't a guarantee, and it isn't a rule without exceptions. But it is a pattern that researchers have observed repeatedly, and it is exactly consistent with what we just witnessed in early March. The significance of this is not just academic. It means that the early arrival of this outbreak was not truly unexpected to scientists who had been watching the ocean. It was anticipated in the broad strokes, even if the specific timing and location were only narrowed down in the final days. The atmosphere was already behaving in the way that ocean scientists had been tracking for weeks, and yet even with the La Niña transition fully on the table, even with the warm anomalies building, there was still something else contributing to this pattern. Something that doesn't get discussed in typical weather coverage because it operates in a realm that most people never think about: the stratosphere, approximately 30 miles above the surface of the Earth. And something was happening up there that had been quietly reshaping the behavior of the jet stream for weeks before the outbreak. And when you understand what that event was, the picture of this outbreak and what it means for the weeks ahead becomes complete. You probably didn't hear about this. Most weather coverage doesn't go there. It's not visible, it doesn't generate storm footage, and its effects take weeks to ripple down to the surface where you and I actually live. But in the weeks leading up to this outbreak, something was happening far above the clouds, far above where commercial aircraft fly, far above where weather as most people think of it even exists, and that event has been one of the most significant and underreported drivers of the atmospheric pattern that produced what we just saw. The event is called a sudden stratospheric warming. The stratosphere is the layer of the atmosphere that sits above the weather-forming layers we're familiar with. Under normal conditions, the stratosphere in winter is home to a powerful ring of cold, fast-moving air that circles the polar regions a structure scientists call the polar vortex. When that ring is strong and intact, it acts like a lid on the atmosphere. It keeps the coldest Arctic air contained at high latitudes and helps the jet stream maintain a more organized westerly flow. That organized flow, in turn, keeps the weather patterns over North America in a relatively stable configuration. When the stratosphere warms suddenly, and that warming can happen with extraordinary speed, over a matter of days the polar vortex weakens. The ring of fast-moving air loses its coherence. It can stretch, distort, and in the most dramatic cases, actually split into separate pieces. And when that happens, the lid comes off. The jet stream, no longer anchored by a strong polar vortex above it, begins to meander in large, looping patterns. It pushes far southward in some areas and northward in others, creating the sharp contrast between cold and warm air that, combined with a warm lower atmosphere, set the stage for a major outbreak. In early 2026, scientists confirmed that a major sudden stratospheric warming event was underway above the Arctic, an event that multiple research teams and meteorological organizations had been tracking since midwinter. severeweather.eu reported that the stratospheric wind reversal was forecast to begin in the first days of March. The polar vortex was splitting a development atmospheric scientists described as exceedingly rare for this time of year. Multiple science news outlets reported on what researchers were calling a major sudden atmospheric event with real consequences for the weather pattern across the United States. The downstream consequences are the critical piece. A sudden stratospheric warming event doesn't turn on a tornado. The distance between the stratosphere and the surface is enormous, and the pathway from stratospheric disruption to surface weather is not a direct one. What it does is reshape the environment in which surface weather operates. It bends the jet stream into configurations it wouldn't otherwise take. It sustains those configurations for longer than typical weather patterns would last. It essentially changes the rules of the game the surface atmosphere is playing, making certain setups more likely to persist, more likely to intensify, and more likely to occur at unusual times in the seasonal calendar. That is precisely what happened here. The stratospheric warming event that developed in late winter did not cause this outbreak directly. What it did was create the atmospheric environment in which an outbreak in early March became possible. It removed the high-altitude organizational structure that normally keeps the jet stream from making the kind of sharp, southward dive that compressed warm and cold air into the zone over the central United States. Without that structure in place, the atmosphere was free to organize in ways the calendar alone would tell you it shouldn't be ready for yet. What makes this particularly significant is the timing of the effect. The relationship between a stratospheric warming event and its surface weather consequences typically plays out over a period of several weeks after the event peaks. This means the disruption that began developing in late winter would have been exerting its influence on the surface pattern at exactly the time this outbreak formed. The jet stream was already being reshaped by forces set in motion well before anyone was tracking this outbreak on a weather map. Researchers confirmed in early March 2026 that a rapid warming and weakening of winds high above the Earth had disturbed the polar vortex, with consequences for the weather pattern expected in the weeks ahead. Weather organizations confirmed that the effects of this polar vortex disruption were expected to continue shaping the forecast through March and into spring. These reports were documenting something real, something that, when combined with the La Niña transition and the pre-existing warmth anomalies, created a convergence of atmospheric forces that pushed the season's first major outbreak into early March. Here is what this means for the broader picture. A sudden stratospheric warming event of this magnitude doesn't resolve itself in a single week. Its effects can persist in the atmospheric circulation pattern for several weeks after the peak, meaning the outbreak on March 6th may not be the only significant weather this pattern produces. Scientists looking at this pattern have noted that when the jet stream is in this kind of displaced amplified configuration sustained by stratospheric disruption, it tends to create what they call a locked pattern, where similar conditions can recur multiple times over the same region. Research on past stratospheric disruptions shows that the jet stream doesn't always return to a stable pattern immediately after a major outbreak. In some cases, conditions can reset and redevelop within weeks. And there is one more layer to this story that is not getting the attention it deserves. Even within the atmospheric setup just described, warm air, jet stream displacement, La Niña exit, stratospheric disruption. There was a specific characteristic of the outbreak that made it more dangerous than the atmospheric science alone would suggest. It wasn't just when the outbreak happened, it was what time of day it happened. And the science behind that is something that should change the way every person in a severe weather-prone area thinks about their own risk. Not just for this event, but for everyone that follows. Most of us sleep at night, and that single fact is the most important variable in understanding why the Oklahoma strikes from this outbreak were so dangerous, and why nighttime severe weather events are, from a purely scientific standpoint, one of the higher risk combinations in atmospheric science from a human safety standpoint. The tornadoes that moved through Oklahoma in the overnight hours were not necessarily stronger than tornadoes that strike during the day. The physics of atmospheric rotation doesn't change based on the hour. What changes is us. The human side of the equation, the warning to response chain that saves lives during daytime events, breaks down in the dark in ways that are measurable, documented and taken very seriously by researchers who study tornado fatalities. Published research on nighttime tornado vulnerability is clear on this point. The proportion of tornado fatalities occurring at night has been rising over time, even as daytime fatality rates have improved steadily through better forecasting and warning systems. Studies show that nocturnal tornadoes, those striking between late evening and early morning hours, are associated with a fatality rate nearly twice that of daytime events. The reason is not the storm. The reason is the gap between when a warning is issued and when it actually reaches someone who is asleep, without the television on, without notifications cutting through deep sleep, without any of the environmental cues that naturally heighten awareness during daylight hours. Research published in peer-reviewed atmospheric science journals found that nocturnal tornadoes produce fatalities at a meaningfully higher rate compared to their daytime counterparts. National Geographic has reported that nocturnal tornadoes are becoming more common as climate patterns shift the timing and location of severe storms, meaning this is not just a historical curiosity, but an active and growing component of the overall risk picture. What makes this scientifically interesting and worth understanding beyond just this one event is the layered nature of the warning gap. During a daytime severe weather event, people are awake. They are actively monitoring. The social network of awareness, a neighbour calling, a co-worker checking the weather, someone noticing the sky functions as a distributed warning system that supplements official alerts. At night, that network collapses. People are isolated by sleep, by silence, by the darkness that removes the visual environmental signals that normally support the official warning infrastructure. Additionally, research has shown that people are less likely to receive a tornado warning at night simply because the warning delivery mechanisms that are most effective, television broadcasts, visual alerts, community-wide attention to the weather, are largely inactive in the overnight hours. A phone silenced during sleep may not deliver a warning in time. Researchers who study tornado safety say that understanding how warnings reach you at night is one of the most practical steps anyone can take. The Oklahoma overnight strikes from this outbreak unfolded in exactly this context. People were asleep. The warning window was compressed. The darkness removed the environmental cues that give people even a few additional seconds of awareness. Research shows that the same atmospheric conditions produce a higher fatality rate when storms arrive at night compared to when they strike during the day. Here is what the research is actually showing over time. The shift in tornado fatality patterns toward the nighttime hours is not random. It is connected to the same broader pattern shifts that moved this outbreak into early March. As the timing and geography of severe weather events evolve, the nighttime component among the highest risk from a human vulnerability standpoint is becoming more significant, not less. This is not a call to panic, it is a call to pay attention. Nighttime severe weather preparation, understanding your warning systems, knowing what alerts will actually reach you when you're asleep. Having a plan that doesn't require being awake to execute is one of the most concrete and actionable pieces of knowledge that comes out of the science of tornado vulnerability. And it is dramatically underemphasized in most weather coverage. But the nighttime factor is only one part of a larger shift scientists are actively tracking. The Oklahoma strikes happened at night in a state that has always been on the severe weather map, in a place where tornado preparation is part of the cultural fabric. Researchers say the growing concern is nighttime storms arriving in areas where people have little experience with severe weather communities that are newer to this kind of risk and may not have treated it as a priority until now. The map, it turns out, has been quietly changing for years, and the new version looks nothing like the one most people have in their heads. There is a mental map that most Americans carry when they think about tornado country. It looks roughly like a vertical band running down the center of the nation Texas up through Oklahoma, Kansas, Nebraska, the Dakotas, the iconic corridor that earned its name from decades of documented outbreak activity, the place that, in the cultural imagination, is where tornadoes happen. That map is no longer fully accurate, and the science showing why it's changing has been building in peer-reviewed research for years, quietly, methodically, without making the kind of headlines that the outbreaks themselves generate. The result is a gap between what the public believes about tornado geography and what the data is actually showing, a gap that may be the most important thing anyone living east of traditional tornado country needs to understand right now. Scientific American reported on this shift explicitly, noting that tornado outbreaks are moving from the Oklahoma and Texas heartland eastward toward Tennessee, Kentucky, and the broader southeast. The research they cited based on decades of outbreak data showed that the nucleus of large tornado outbreak activity has been shifting eastward over a span of more than 30 years. This is not a single anomalous season. This is a documented multi-decade trend. Researchers studying the geographic distribution of tornado activity have found that the traditional Great Plains zone has seen a decrease in large outbreak frequency, while states across the southeast Arkansas, Mississippi, Alabama, Tennessee, Louisiana, Kentucky have seen a corresponding increase. Experts quoted in Fox 19's coverage of the shift described it as a movement of tornado-producing patterns from the classic alley toward what scientists sometimes call Dixie Alley, a zone running through the south-central and southeastern United States. Scientists have identified two primary drivers behind this geographic shift. The first is a long-term drying trend in the Western Plains. The Great Plains outbreak machine has always relied on a specific fuel source, deep moisture flowing northward from the Gulf, combining with dry air descending from the Rocky Mountains. When drought conditions persist across the western and central plains for extended periods, that moisture-dry air collision zone moves eastward to where moisture can still be found in sufficient quantities. The storms follow the fuel. The second driver is the broader shift in atmospheric circulation patterns that has been reshaping where and when the jet stream creates favourable severe weather setups. As the jet stream's preferred position and behaviour evolve over time, the geographic corridor where it most frequently creates the kind of north-to-south atmospheric clash that drives outbreak conditions has gradually tracked eastward. The result is that states in the southeast and mid-south are experiencing severe weather setups that, a generation ago, were far less common in their historical record. What makes this particularly significant from a public safety standpoint is a characteristic of the southeast that researchers emphasize repeatedly. The terrain, the housing stock, and the cultural preparedness infrastructure in the eastern zone are fundamentally different from the Great Plains. In Kansas and Oklahoma, severe weather awareness is built into daily life. People know the sirens, they have basements, they have practiced responses. The landscape is open, which means tornadoes are more visible, and warnings give people more lead time. In the southeast, much of this is reversed. The terrain is heavily wooded, which means a tornado can be travelling through a forest and be completely invisible until it reaches a clearing. Large portions of the housing stock in affected areas consist of mobile homes and older structures that are far more vulnerable to wind damage than the solid construction common in the plains. And critically, the cultural framework of severe weather preparedness that has developed over generations in traditional tornado country is simply less established in places that didn't think of themselves as tornado country until relatively recently. Research has specifically documented this dynamic, noting that the eastward shift of tornado-prone zones is moving activity into communities that may not be prepared physically, culturally, or psychologically for the kind of severe weather now arriving with increasing frequency. The combination of more vulnerable housing, less established warning culture, and more visually obstructed terrain creates a risk profile that is in some ways more dangerous per storm than the classic Great Plains zone, even if the absolute number of events per year is lower. Meteorologists who have been studying the shift have noted that states like Arkansas are now significantly more prone to tornadoes and severe weather than their historical records would suggest, and that the trend is ongoing, not a temporary fluctuation. AccuWeather has similarly documented the shift, noting that the nucleus of large outbreak activity has been moving southeast over the span of recent decades, with the most recent years showing continued movement in that direction. This is the context that makes the early March outbreak more significant than a single event story. The storms that struck Oklahoma this week struck a state that has always been inside the severe weather zone, a state with a history and a preparedness culture built around exactly these events. But the pattern that produced those storms is the same pattern that, as it continues to evolve, will increasingly bring severe weather to communities that have less experience with this kind of risk, fewer protective structures, and less established awareness of severe weather threats. The people of Tennessee, Kentucky, Mississippi, Arkansas, and the broader Southeast are not necessarily aware that the atmospheric forces that once concentrated their worst energy over the Great Plains are now, according to the data, spending more time over their region. That awareness gap is one of the most consequential and underreported stories in atmospheric science, and it is directly connected to the forces that drove the early season outbreak we just witnessed, which raises the final and most important question that this entire investigation has been building toward. If the map is changing, if the season is arriving earlier, if the stratosphere is disrupted and the ocean is transitioning and the geographic distribution of risk is shifting, what are scientists actually forecasting for the rest of spring 2026? What does the data say is coming? And where does the confidence end and the honest uncertainty begin? Let's bring all of this together, because everything we've discussed, the early season warmth, the the jetstream displacement, the La Niña transition, the stratospheric disruption. The geographic shift was not happening in isolation. These were simultaneous forces converging at the same moment, producing the same result. The question now is whether those forces have spent themselves in this single early March outbreak, or whether the conditions that produced it are going to persist into the weeks and months ahead. The honest answer is that scientists are more confident about the pattern than they are about the precise timing and location of individual events. That distinction matters, and any responsible forecast has to hold it clearly. Forecasters can tell you a great deal about the atmospheric environment that spring is building toward. They cannot tell you with certainty which specific days will produce the next outbreak, or exactly which areas will be in the path. But the broad strokes picture for spring 2026 is something that AccuWeather, NOAA, and independent research teams have been constructing all winter, and what they're seeing is significant. AccuWeather's spring 2026 forecast was built around the central finding that the rapid exit of La Niña, combined with the evolving atmospheric circulation patterns, would create a season that looks different from recent years. Their severe weather outlook noted tornado chances above the historical average, with forecasters expecting activity to gradually increase through the core spring months. The La Niña transition is the biggest single variable. NOAA's Climate Prediction Center confirmed that the transition from La Niña to neutral conditions was expected to complete within the late winter to early spring window. As that transition progresses, the atmospheric bias that mildly suppressed severe weather frequency during La Niña continues to erode. The atmosphere becomes increasingly receptive to the kinds of setups that produce significant outbreak conditions not on every day, but with greater frequency than a fully established La Niña would typically allow. AccuWeather's long-range team specifically noted that the spring pattern would be shaped by what they described as a slower jet stream, one that, rather than racing eastward in a tight organized band, meanders more broadly, creating larger amplitude waves that dig further southward and surge further northward than normal. A slower, more amplified jet stream is almost always associated with increased severe weather potential across the central and southern United States. It is the atmospheric configuration that creates the sharpest boundaries between contrasting air masses, and those boundaries are where the atmosphere's energy concentrates. The stratospheric disruption adds another layer. Because the effects of the polar vortex split typically take weeks to fully propagate through the atmospheric column, the influence of the late winter stratospheric event is likely still working its way through the system as spring builds. This doesn't mean every week will produce outbreak conditions. What it does mean is that the jet stream is operating in a more erratic, less organized mode than it would be in a year without a stratospheric disruption, making the atmosphere more susceptible to sudden reorganizations that can produce rapid, severe weather setups. AccuWeather forecasters signaled that severe storm chances for the full spring season would come in slightly above average, with tornado chances specifically tracked as above the historical norm. Their overall season forecast projected a range of activity suggesting the early March outbreak fits more closely with the forecast pattern than with a one-time anomaly. The atmospheric conditions that made early March possible have not fully resolved. Forecasters say those same drivers above normal warmth, an unstable jet stream pattern, and the ongoing La Niña transition are expected to remain active as spring continues. NOAA's seasonal outlook for the spring period confirmed the broad strokes of this picture. The probability distributions for temperature and precipitation patterns were consistent with the kind of active severe weather regime that correlates with above-average outbreak frequency in historical records. Warmer than normal temperatures across the southern tier of the country, combined with the evolving jet stream pattern, are to create the fuel for an atmosphere that continues to produce significant severe weather events into April and May. Here is where the honest uncertainty has to be stated clearly, because any forecast that doesn't acknowledge it is giving you false confidence. The specifics are not known. The atmospheric science gives us a framework, a pattern, a tendency, a probability distribution. It does not give us a calendar. The difference between a season that produces a handful of notable outbreaks and one that produces a historically active spring often comes down to the precise timing of individual weather pattern setups, something no model can predict reliably at the multi-month range. What the science is saying with reasonable confidence, the atmosphere has been primed for an active early spring. The forces driving that priming ocean transition, stratospheric disruption, Jetstream behavior are ongoing and consistent with a pattern that historically produces elevated severe weather activity. The geographic distribution of that activity is tilted, as the longer-term research shows, somewhat more toward the eastern and southeastern portions of the country than historical norms would suggest. What you can take from all of this is that the spring of 2026 deserves your attention. Not fear attention. There is a meaningful difference. Your fear responds to a single event and then recedes. Attention persists, stays calibrated, and remains useful long after the headlines have moved on. And the reason that attention matters this spring more than any individual forecast can capture is the bigger picture that this entire investigation has been pointing toward all along. Let's look at what this moment actually represents, because it is more than a single early outbreak. It is a data point in a story that has been accumulating for decades. The early March outbreak was the result of multiple atmospheric forces arriving at the same time, not a single cause, but a convergence of documented patterns. A geographic shift moving storm activity toward communities less prepared for it, and a season that started early not by coincidence, but because the underlying drivers had already shifted. None of these forces appeared without warning. Scientists had been tracking each one: the ocean transition, the stratospheric disruption, the geographic shift in tornado activity long before this outbreak formed. The gap is not in the science. The gap is in how the science reaches the people who need it most. The people who live in the new tornado zones who don't know yet that their region is now in a different category of risk. The people who have good warning systems but sleep through them because nobody told them that a nighttime outbreak is a fundamentally different kind of danger. The people who understand that broader patterns are changing but haven't connected that to the specific present tense way it is reshaping the risk profile of their own backyard. What comes next, in the atmosphere, is still being written. The forces in play are well documented. The broad pattern for spring 2026 is above average energy, an evolving jet stream, a geographic distribution of risk that extends further east than most people expect. The exact dates and locations of what that pattern produces remain unknown. Nature always reserves the final word on the specifics. But here is what is worth carrying forward from everything we've covered. Early outbreaks are one of the signals forecasters watch carefully when assessing the character of the season ahead, not as a guarantee, but as a signal. As the atmosphere's way of showing you what it's capable of before the heart of the season even begins. The early March outbreak was that kind of signal driven by real forces, arriving for real reasons, and pointing forward into a spring that, by every measure scientists currently have, deserves to be taken seriously. If you found this investigation valuable, share it with someone who would benefit from knowing. Subscribe if you haven't already. And leave a comment below telling me where you're watching from and what question this raised for you, because your question might be exactly what the next investigation is built around. The science behind what comes next this spring is worth staying close to, and this channel will continue covering it as the season develops.